So we were going by the Gauss-Markov theorem, and till now what we have proved that this beta, this the regression slope coefficient or the parameter, it is linear and it is unbiased. So these two things we have done till now regarding the Gauss-Markov theorem. Now the third thing which we need to prove is that this beta hat is having the minimum variance. This will prove, if this is done, then we will say that our estimator is blue, best linear unbiased estimator. Now the variance of beta hat, we can write it as the variance of beta hat, it can be written as expected value of beta hat minus expected value of beta hat, bracket closed, raised to the power 2. Now we have seen that expected value of beta hat is nothing but b. Here we have proved, when we were proving that this is an unbiased, beta hat is an unbiased estimator, it was proved that beta expected value of beta hat is equal to beta. So similarly, what we are doing, this expected value in place of expected value of beta hat, we are simply writing b. So variance of beta hat, it can be now written as expected value of beta hat minus beta square. Now beta minus beta hat, this also we have earlier seen that this is equal to summation wi ui. It can be seen, we have done in our previous calculation. See over here, it shows that we have proved that beta hat minus beta is equal to summation wi. So we use this over here, this information over here. So in place of beta hat minus beta, we simply write it, in place of this we simply write it as summation wi ui. Now we have this term, expected value of summation wi whole square. This we can, by using this we can write it as, because this is wi ui, I, it will be 1, I can be 2, I can be 3. So this thing is written as, when we open up and remove, when we can open up and say, this can be written as w1 u1 plus w2 u2 plus w3 u3 plus, likewise you can extend it up till wn un raised to the power 2, that is I is equal to 1 to 3, and we can extend it. Now we can use the basic formula of a plus b plus c whole square. We can use that formula, a plus b plus c whole square, which is equal to a square plus b square plus c square plus 2 bracket open ab plus bc plus ca. Say a plus b plus c whole square is equal to a square plus b square plus c square plus 2ab plus bc plus ac. So this is, using this formula, we write this term as w1 square u1 square plus w2 square u2 square plus w3 square u3 square, extend up till wn square un square plus 2 w1 w2 u1 u2 plus 2 w2 w3 u2 u3. So I repeat, this can be written as plus 2 w1 w2 u1 u2 plus 2 w2 w3 u2 u3, and this can go on to extend for the nth term to wn minus 1 wn un minus 1 un. Using we are using this formula. Now this can be summarized as 2 summation ui square. Now instead of putting 1 2 3, so here I is equal to 1 to n. I is equal to 1 to n. So 2 summation yi square ui square plus 2 summation j summation I wi wj multiplied by uj ui, where j starts from 2 and extends up to n. So this particular term we are writing it as this. Now what is w? W consists of x. If we go to our previous slides, we have in our discussion we have started that wi. We started wi is equal to xi divided by summation xi square. So this is our wi. Now we can say as w consists, now see this we can write it as this thing uj. If you remember the classical linear regression model, we say that there is no relationship between the error of one point at the error with the error at the other point. So this becomes 0, this entire term becomes 0. So what is left is this. Now this we can write it as sigma square summation wi square. Summation wi square is as it is, and this ui square, the expected we can say is equal to sigma square, the variance. So now using the assumption ui and uj is equal to 0, that becomes 0. So finally the variance of beta hat is equal to sigma square multiplied by summation wi square, and summation wi square is equal to sigma xi square. So we see that wi is made of values of x, and x are given, hence we cannot change it. Further we can't change the value of wi. So in order to prove that this has the minimum variance, since we cannot change it, xi is given. If you remember our discussion, xi's are fixed. At the income level, with a particular level of income, there can be different consumption expenditure. Same income level of 90, some family may consuming 60, some family may consuming 75, but that 90 remains the same. So we take another hypothetical estimator, and then we will see the minimum variance. So we take another estimator. Now it's not beta hat, because we are taking another estimator beta double hat. So earlier beta hat was equal to summation wi. So now we denote this beta hat by summation ci yi. Ci is nothing but an arbitrary constant. Now here what we will do, you will first prove that this hypothetical estimator is also linear and unbiased. So we have to prove that expected value of beta is equal to beta double hat. The expected value of beta is equal to beta, and that beta hat has the minimum variance. So now we go for the proving of the minimum variance for our new variable. So we have this regression equation, yi is equal to alpha plus beta xi plus ui. Now we have using the same logic as earlier, we say that beta double hat is equal to summation ci yi is this. So we incorporate this term. So we can write it beta double hat is equal to summation ci alpha plus beta xi plus ui. So when we open the bracket, we get this term. This says beta double hat is equal to alpha summation ci plus beta summation ci xi plus summation ci ui. So now we have proved that this is linear. Now it will be unbiased provided two conditions are satisfied. Beta double hat, it will be an unbiased estimator provided the two conditions are satisfied. The first one is summation Ci is equal to 0 and summation Cixi is equal to 0. If you recall, in our earlier case when we are using Wi, summation Wi is equal to 0 and summation Wixi was equal to 1. So here also it will be an unbiased if both of the same condition holds over here as it was over there. Let us assume that these two conditions are satisfied. Then we can write that beta double hat is equal to alpha summation Ci plus beta summation Cixi plus summation Ciui. When we take this, now Ci, this is 0, Cixi, this is 1. So we can say that beta double hat is equal to beta 1 beta, or you can say it beta plus summation Ciui. So beta double hat is equal to beta plus summation Ciui. Now we take expectations. So the expected value of beta double hat is equal to beta, because beta the expectation will be the same, plus summation Ci expected value of ui. And now we know by the assumption that expected value of ui is equal to 0. So this whole term, it becomes 0. So what is left is expected value of beta double hat is equal to beta. So we got the feeling that it is linear, it is unbiased. Our new estimator is also having the same properties. Now we move to the minimum variance. What is variance? Variance of beta double hat is equal to expected value of beta double hat minus expected value of beta double hat whole raised to the power 2. So we have seen that expected value of beta double hat is nothing but is equal to b. So we can write the same, that is equal to expected value is expected value bracket beta double hat minus beta whole square, and this is nothing but which we have just now seen in our previous discussion. This is from here we can write it. From this we can write this is nothing but equal to expected value of summation Ciui. Now, using the same logic which we have used earlier, the formulas, the same thing, we can open this term and write it as expected value of summation Ciui square plus 2 summation I summation j Ci Cj Ui Uj. The same logic which we have seen over here. I am referring to this one. The same logic using the same formula, we can write it like this. Now, so this can be written as, we take Ci outside, so expected value of ui square plus 2 summation I summation j Ci Cj Ui Uj. Now, when we take the expectation, the expected value of Ui Uj, it becomes 0. The expected value of ui uj, here the expectation sign is also be there. So this entire term, it becomes 0. So what is left is variance of beta hat is equal to summation Ci e ui expected value of ui square. This can be written as sigma square summation Ci whole square. This is nothing but the variance of your new estimator beta double hat. Now, again, we are free to choose any value of C that can minimize the variance of beta double hat, but this is not a case of free minimization, because we have earlier made two conditions. So now what we will be doing, we will be using our knowledge of Lagrangian multiplier in order to find the further, we will form the Lagrangian function. The only thing is we are doing is, instead of multiplying by the Lagrangian, instead of using alpha, lambda and mu, we are doing it by 2 lambda and 2 mu. So we can write is as the Lagrangian function as theta is equal to summation ci square minus 2 lambda summation ci minus 2 mu summation ci xi minus 1, because we have just now modified it. So this is your Lagrangian function. So we will try to minimize the variance. Okay, we start with the Lagrangian function, which reads at theta is equal to summation ci minus 2 lambda summation ci minus 2 mu summation ci xi minus 1. Now, what we have over here is we differentiate it first with reference to ci. We get this term summation 2 ci minus 2 lambda minus 2 mu xi is equal to 0. Next time we differentiate this equation with respect to lambda, so we get this function minus 2 summation ci is equal to 0, and then we differentiate this function with respect to mu. So this is equal to minus 2 bracket open summation ci xi minus 1, that is equal to 0. We take the first over here. We write it as 2 ci minus 2 lambda minus 2 mu xi is equal to 0. We algebraically manipulate it. So ci minus, that is we divide both the sides by 2, this also and this also by 2. When you divide both the sides by 2, what we are left is ci minus lambda minus mu xi is equal to 0. Now on rearranging, taking these minus terms to the right hand side, what we find is ci is equal to lambda plus mu xi. So ci is equal to, the ci is equal to lambda plus mu xi. What we add the summation signs on both the sides, so this can be written as summation ci is equal to n lambda plus mu summation xi, which is equal to 0. Now summation ci, as we have just assumed earlier, as per the condition, is equal to 0. So this becomes 0. So we can now write n lambda is equal to, we take this to the right hand side, is equal to minus mu summation xi. Summation, now n, we take n to this side, so lambda is equal to minus mu multiplied by summation xi divided by n. This we can say that lambda is equal, summation xi divided by n is nothing but the mean of n, so lambda is equal to mu x bar. Now we have this equation ci is equal to alpha plus mu xi. We have got this equation from here. ci is equal to lambda plus mu xi. We write this equation over here and we substitute the value of lambda over here. So now it becomes ci is equal to mu x bar plus mu xi. This can be, on rearranging this, this is just a repetition of the first term. So on rearranging, what we find, ci is equal to mu xi minus mu x bar, means we write this term first and this term and the later terms. So we can now say that ci is equal to, we take mu common, it is equal to c xi minus x bar. And see, we know by our previous that what is this xi, summation small xi, it is nothing but xi minus x bar, and this term is the same. So we can write ci is equal to mu xi. Now once we have ci is equal to mu xi, what we do, we multiply both the sides by xi. Xi is nothing but xi minus x bar, and if we rearrange this, we write it in terms of xi, we can write it as xi is equal to, this is small xi and this goes over there in the plus sign, plus x bar. So what we do, we write ci xi is equal to mu xi. Now in place of xi, we write what we have just now seen, that is xi is equal to, capital Xi is equal to small xi plus x bar. So now we open this bracket over here, this can be written as mu xi square and this is x bar mu xi. So Cixi, we can write it in this format. Again, x bar is nothing but summation x by n. So that thing we incorporate over here. So Cixi is equal to mu small xi square plus summation capital Xi divided by n multiplied by mu xi. Now see, Cixi is equal to, this is what we will be left with as summation xi. If you remember, summation xi is equal to 0. So now when summation xi is equal to 0, so what we are left is Cixi is equal to mu summation xi square. Now we have this, we already know, we have taken one of the assumptions that summation Cixi is equal to 1. When we have already taken that summation Cixi is equal to 1, we can write it as summation Cixi is equal to mu summation small xi square. Now this is equal to 1. So we can write mu summation xi square is equal to 1. So mu is nothing but mu is equal to 1 divided by summation xi square. So now in Ci is equal to mu xi square, mu is equal to 1 divided by summation small xi square, we have just now proved. So we put the value of mu over here, we put this value of mu over here. So we get Ci is equal to 1 divided by summation small xi square xi. So this is your Ci is equal to xi divided by summation xi square. If you remember, earlier we had wi was also equal to, now this term and this term are same, and this term had the minimum variance. So we can say that our variance is minimum over here, as this value of Ci is the same as the value of Wi. So now so we can say, based on this, we can say that the variance of beta double hat, the estimator which we had taken in place of beta hat, it also has the least variance. So with this, we come to an end to our discussion of Gauss-Markov theorem. The Gauss-Markov theorem, it basically proves the three properties, that the estimator which we have, that is beta hat, is equal to summation xi divided by summation x square. This estimator is having three properties. First, it's linear. Second, it is unbiased. And third, it has the minimum variance. So we can say that this estimator beta hat is blue, best linear unbiased estimator. With this, we end our discussion on Gauss-Markov theorem. Thank you.